you already know deterministic final state automata. That's the first computing machine we learned about. And we saw that it can solve many problems, but not all of them. And particularly, if you have a problem which inherently requires the operation of counting, DFAs cannot help you. Meaning that because they have a finite memory, they cannot implement an open-bounded counting. Meaning that if you have a problem which requires an open-bounded counting, you cannot rely on DFAs. For example, we saw that with the language of balanced parentheses, meaning that for the language of balanced parentheses, you want each open parenthesis to have a corresponding closed one, right? But that requires counting. That requires keeping in memory how many parentheses you opened. And while DFAs can solve that problem for a certain number of parentheses, so if you fix a number, you say, okay, I will never open more than 1,000 parentheses. A DFA with some thousands of states can, of course, solve that problem. But if you want to keep the problem pure and just say, okay, I want to solve this problem for all possible open parentheses, then DFAs are not enough. You need something more. You need a machine that can count and that has an unbounded capacity of counting. Okay? Actually, you need a machine with an unbounded memory that you can use. Now, there's different ways you can implement memory. The simplest kind of memory you can implement is actually a stack. Okay, it's very limited, meaning that it's not random access. Okay, you cannot just read whatever you want in the stack. You can only read the top item. Okay, and it turns out that if you add this simple kind of memory to your DFA, if you give your DFA the ability to read a stack, to push stuff in a stack, to pop stuff in a stack, you have now a machine that can solve many more problems than DFAs. And actually, if you look at this machine and you actually see what kind of problems it can solve, it can recognize all context-free languages. So in the last lecture, I showed you the grammar point of view on language, right? So generating grammars. And we saw particularly context-free grammars, okay, which generate the context-free languages. Well, now we have the corresponding automaton. We have a machine that can recognize all context-free languages. Now, for the actual description. So let's represent. Let's have a different representation than the state diagram I showed you until now, right? Let's see a DFA like some kind of machine with a state control. What's a state control? Here you can imagine you have some piece of hardware which keeps count of what state you are in, and depending on the input you read, this machine here can change the state in memory, right? Which is exactly DFA, right? This is exactly what a DFA does. But let's look at it like a machine reading a tape, okay? So a DFA has a read action, so it can read the tape, and depending on the tape, you change the state in the state control. So now we're adding a stack. So there's more stuff that the DFA can do, which is manipulating the stack, okay? So this machine here, this new machine we're creating, it's called Pushdown Automaton. Pushdown because you get symbols, you push down the stack, okay? So it's DFA plus a stack, and it's a first in, last out access to the memory, okay? So you push something, if you push other stuff, that something is getting buried, and then to get it again, you have to pop all the stuff you pushed. So it's first in, last out, because you have the other ones to pop before, okay? So what are the actions that this machine can perform? Well, of course, it can do exactly everything that a DFA can do, okay? The only thing that you need to do is to leave the memory alone, okay? You just don't use the memory. But it can also manipulate a stack. So, now the state control can read the tape, the input tape, but it can also read the top of the stack. Based on this couple, so based on what's in the tape at that particular moment in time and the top of the stack, you can decide to pop the top of the stack, so you get that symbol, you throw it away, and to push another symbol on top of the stack, okay? So in this case, you pop Y, okay, you read Y, you pop Y, and you push Z, okay? After you did that, so after you manipulated the stack, you're finally free to change state, to go into another state. And that's all a PDA does, okay? So now I'll do some examples so it will be clear to you in a moment, okay? But let's take a transition. The notation we use for a DFA is, okay, this round thing is a state, this round other thing is another state, and you have a transition which depends on reading X. So if you're in state 1 and you read X in your input, you go to state 2. Now you have more things you need to do at every state, okay? You need to read the input, you need to read the stack, you need to manipulate the stack, and then you need to change state. So the notation is like this. This couple here means read the input tape, read the top of the stack. So input tape, top of the stack, pop the top of the stack, and push a Z. Okay, so this corresponds to that diagram up there, okay? So you have X and Y, X in the input, Y in the stack, you pop it, and you push a Z, and then you change state to state 2. So, now, your transition depends not only on the input, but also on the top of the stack. That should be clear. So, there are special cases, meaning that, okay, you can either read the input, or maybe you want to leave the input alone, you don't want to read it. You want to read the stack, maybe you don't want to do that. Maybe you don't want to pop the stack, maybe you don't want to push anything. So you have control on these things, okay? So for example, in the first case, we have the empty string and then Y going to Z. What does it mean? That you don't read any input, you just read the stack, you pop it, and you push at Z. Here, you read the input, you read X, you don't read the stack, but you still push a Z. Here you don't pop anything, because this goes together, okay? So if you have an epsilon here, you're just leaving the top of the stack alone, and you push whatever you have to push, okay? So what's this? Exactly. Push the empty string is also don't do anything. So don't push anything, okay? Here, what does this mean?
No input, no stack, and then push Z.
Exactly. So you don't do anything. The only action you perform here is push the Z symbol on top of the stack. What about this?
Read input X, don't read anything from the stack, and then push Z.
Exactly. So it should be easy, right? So you don't read input. You just read the top of the stack, but you don't do anything to the top of the stack. You don't push anything. You don't do anything. You don't read the input. You don't read the stack. You don't push anything. This is like the empty transition in DFAs, right? This means, okay, just go on with the transition. Don't read anything. Don't do anything. Just do the transition, and that's all. Okay. So now you should be able to read this notation, so I can present to you your first push-down automaton. And we start with the very same problem, which we use to show that DFAs cannot solve all problems. Which is exactly, well, this is not the language of balanced parentheses per se, but it's the language of, you have to have, in this language you have the strings which have the same number of zeros than ones, okay? And zeros are all on one side, and ones are all on the other side, and you cannot use a DFA to solve this problem, okay? You have to use a PDA. So, what is this PDA doing? Well, first of all, so to solve this problem, it requires counting. So a good algorithm will be keep count of all the zeros, okay? And then, because you have a stack, you can push something in the stack. You have a counter, right? So every time you see a zero, you push a stone, an X, whatever, okay? Something that keeps count, okay? So let's say you see 8 zeros, you push one, so you see 8 zeros. You push one stone, you push another, you push another, push another, push another, push another, push another, push another. Now, you want to be sure that there are at least as many ones as there's zeros you saw. So what you do, you pop, you pop, you pop, you pop. Every time you see a 1, you pop, okay? So you're sure that if you reach the end of the stack and you don't read any input, you have as many ones as zeros, okay? And that's exactly what's happening in this PDA. So initially we push a special symbol in the stack. So the stack is empty. We push a special symbol, the dollar symbol. Doesn't matter, okay? Normally it's the dollar. So if you see the dollar now, you remember that what it's signifying is just saying, okay, I push a symbol so that I remember where I started, okay? So that symbol means, if you encounter that symbol later in the computation, it means, okay, you reached the end of the stack. You popped everything you could pop, now the stack is empty. You're now seeing the symbol you pushed in the beginning. Okay? So you push the end of the stack symbol, and you start pushing zeros. Every time you see a zero, so if you read 0, you don't read anything from the stack, you just push a 0, okay? And you do this every time you meet a 0. So if you're here, you meet the first 0, you push, 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 push. Your stack now has 8 zeros, okay? Then, at some point, you read a 1. When you read a 1, and there's a 0 on top of the stack, so you push your zeros in the stack, right? If there's a 0 on the top of the stack and you're reading 1 from the input, you pop. You pop the 0, okay? And you do this for every time you read 1 in the input and you have 0 in the stack. So let's say, well, as I said, if you have 8 zeros and 8 ones, you will put all of the zeros. You will pop all of the zeros, and at a certain point, you will read the dollar sign, which is signifying, okay, you reached the end of the stack. And that means you can accept, meaning that you don't have any input anymore, you popped everything, so apparently your zeros are the same number as the ones. What happens if I input, for example, a string like 0, 0, 1, 1, 1, or as a second case, 0, 0, 0, for example, 1, 1, okay? So in the first case, I have more ones than zeros, and in the second case, I have more zeros than ones. So let's see the first case. So I push the end of the stack symbol, so I have it there. Then I start pushing zeros. Tack, tack. My stack has now 2 zeros pushed. And here I read a 1, so I push the zeros. I'm reading now a 1, and there's a 0 at the top of my stack. I pop it. Again, I read a 1, I pop 1, 0. Now my stack is empty, but I'm reading a 1, but there's no transition here to tell me what happens if I have a 1, I'm reading a 1, and my stack doesn't have anything, not even the end of stack symbol. So because of that, my program crashes. So my PDA is saying, there's nothing I can do here. I can't certainly go to the accept state, so I'm rejecting. Okay? Same goes for the second example, right? So I'm here at the beginning of the string, right? I'm not doing anything. The first thing I do is push the $sign. So this is my stack. This is my input stack, just to say. So I'm here, I push the $sign. I'm now in the pushing state. So I want to push my 0. So first 0 read, I read a 0, I push a 0 onto the stack. I read a second 0, I push a second 0. I read a third 0, I push a third 0. I'm now reading 1, so I need to take this transition here. Okay? So because I'm reading 1 and there's a 0 at the top of the stack, I pop that 0. So, okay? Again, I'm reading a 1 now, and I need to pop another 0. I think I cancelled 2. Yeah, sorry. Just, that was about to be a catastrophe. So I read second 1, and I pop the second 0. Sorry. So I'm left with a 0, right? So I am now at the end of my string. There's nothing to read anymore, but I still have a 0 in my stack. And there's nothing telling me what to do with that 0, okay? I don't have any 0, comma, something transition. Sorry, I don't have any something, comma, 0 transition. So there's nothing telling me what to do with this. And because of that, of course, my program is crashing and I cannot go to the accept state. Okay, so we solved that problem with this simple PDA. Let's see another example. This is a nice language. This is the language of palindromes which don't have a middle symbol. I'll tell you in a second what that means. It means, okay, I have palindromes, so if you take the beginning of the string, the first half of the string, and you mirror it on the other side, that's a palindrome, meaning that if you read it left to right, you read something, and if you read it right to left, you read exactly the same thing, like Anna. Anna is a palindrome, for example. Otto is a palindrome. 0110 is a palindrome. 1010, 0101 is a palindrome. I think you see what this is, right? So this is the language of palindromes. It seems like something a PDA can solve, and in fact, it can. How does it work? You just push your symbols in the stack, and when you reach the half of the word, so let's write this down. So let's say that you have 10100101, and you want to accept this. Then you start pushing, right? So you read 1, you push it. You read 0, you push it. You read 1, you push it. You read 0, you push it. And then you do the inverse. You read 0, you pop it. You read 1, you pop it. You read 0, up. You pop it. Up. You read 1, you pop it. And then you're left with an empty stack, and the input is finished, and then you're happy because you're accepting. Okay? That's the strategy you could use. That's one strategy you could use to recognize palindromes. Okay? There's a problem. So this algorithm seems very clever, but you need a way to recognize when you reach the middle of the string, right? So you have to say, okay, now I'm in the middle, I can start popping. I pushed until now I pop because I reached the middle of the string. So you can go about this in two ways. Either you cheat, so you modify your language, for example. So instead of being x reversed, your language would be something like x, I don't know, some symbol at x reverse. So that when you reach that at, your PDA now knows that you reached the middle of the word, and you can start popping. So here, okay, you push the end of stack symbol, you start pushing, 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 until you reach the at. So if you read at, you don't do anything to the stack, you just go and start to pop. Okay? So if you read a 0 and you have a 0, you pop. If you read a 0 in the input and you read a 0 at the top of the stack, you pop the top of the stack. If you read a 1 in the input and 1 in the stack, you pop that. Okay? So you start popping, and if your word is a palindrome, you will end up here, because in the end you end up with an empty stack, you find the end of the stack symbol, and you accept. Okay? What happens if I have strings which don't respect this language? Let's say you don't have an at, okay? Then you never take this transition, so you can never go in the exit state. Let's say you have something, okay, this is a palindrome, let's add 1 in the end, okay? Let's add. So what happens if it's not a palindrome? You push, you push, you push, you push. So you push a 1, so you're here, you push at end of stack. You read a 1, you push a 1. You read a 0, you push a 0. You read a 1, you push a 1. You read a 0, you push a 0. Now, you read an at, so you're here, you go and start the popping procedure. So you start to pop, you read a 0, you pop the 0. You read a 1, you pop a 1. You read a 0, you pop a 0. You see where this is going. You read a 1, you pop this 1. And then you read a 1, and your top of stack is end of stack symbol. And you don't have anything here to tell you what to do. So your stack is empty, but you're still reading something. And that's weird, and you don't accept. Your PDA doesn't know what to do here, so it just crashes. Okay? Are there any questions?
What happens if the middle of your string is a character? So, like race car, for instance, the E is actually the middle of the string.
Mm-hmm. The empty string, you mean?
Yeah.
Well, fact is, the empty string is not part of the input symbols. Okay? The empty string is something you use in your machine, so it's part of your machine construction. Okay? But in your alphabet, you don't actually have the empty string. Okay? So, well, because actually, from the point of view of the machine, this string here, for example, is exactly the same as this string here. Because the machine uses the epsilon to do something between a read and the other, or just to say, don't perform an action in this case. Okay? So it's something of the machine, not the input, symbols. It's not the input alphabet. But your question is actually pretty good. So meaning that, what if I have a 0 here? Okay. What if I have a 0 here? Okay. This certainly is a palindrome. Okay. Because you read like this: 1 0 1 0 0 0 1 0 1 0. Oh, sorry. 1 0 1 0 0 0 1 0 1. 1 0 1 0 0 0 1 0 1. You read it in one side, it's the same as you read it on the other side. So this is a palindrome. And it turns out that you can create a PDA to compute that palindrome, okay, to accept that palindrome. But we're adding something now. We're adding non-determinism. So, because your PDA doesn't have any mechanism to say, okay, I reached the middle of the string, right? Because all your PDA is knowing is that some symbols are getting in the input, okay? So what to do? Well, one possible procedure will be Well, okay, you don't know where the middle of the symbol is, so every time you read a symbol, try and see if that is the middle of the symbol. So try start and pop stuff, and if you reach the end of the stack, you mean that you have a palindrome now, right? And if you don't, it means that, well, first, it could be that symbol you thought it was the middle, it's not, or simply your string is not a palindrome. I'll show you now what this means, right? So we cheated, we added the @ symbol, okay? But really, that's cheating. And the language is not the language of palindrome with a @ in the middle, it's something else. So what to do? We have non-determinism. What does it mean? Well, we met non-determinism already in DFAs, and what non-determinism is, non-determinism gives you a way of spanning new processes, right? So do things in parallel, check if anything accepts. If nothing accepts, then reject. But if a branch accepts, then accept, okay? So what does it mean? That if I add now, I now add a, let's do it color-coded, something like these. Now what's happening? At every step of the computation, you span a new process. So here, what this is saying is, just take the transition every time you can. Don't do anything. It doesn't matter what you have in input. It doesn't matter what you have in the stack. You don't have to do anything to the stack at all. You just have to take this transition every time you can, right? So, okay, I'll first talk a little bit more about non-determinism, and then we return to that example. So, we know, let's have it like this. So we know that non-determinism in DFAs is actually, we could say, syntactic sugar. Meaning that if you have a non-deterministic finite state machine, you can convert it back to a deterministic finite state machine. They're completely equivalent. You have an algorithm, you take an NFA, and you map it back to a DFA. So they're actually the same object. They recognize the same class of languages. You don't add anything computationally by adding non-determinism to DFAs. This is not true for PDAs, for pushdown automata. This is actually false. So deterministic PDA recognize deterministic context-free languages, or LRK languages, which are actually pretty important because it's the kind of languages you want if you want to design a programming language, as I told you last time, because they're predictable, they're deterministic, okay? You will never have ambiguity there. That languages are always non-ambiguous. But deterministic PDA cannot tap into all the computational power you need to recognize the whole set of context-free languages. So to recognize the whole set, you need something more. You need, okay, the stack, but you also need to span how many processes you need to recognize those strings. So actually, the set of context-free languages, it's recognized by non-deterministic PDAs. If you only have deterministic ones, you don't cover all the set. If you have non-determinism, okay, you're fine. You can recognize whatever language you have in your context-free. If you have a context-free languages, you're certain that a non-deterministic PDA will recognize it. So, actually, well, the way you add non-determinism is to have two transitions, for example, many transitions, starting from the same state with the same reading. Meaning that, well, I'll show you the examples. All of these transitions they start all together. So this state here, if you have X as an input and Y top of the stack, so your reading is XY, right? If you have that, all these transitions start together. Why? Well, the first transition says, if you have a reading of X and Y, do something to the stack and then go to S1. The second one says, don't read the input, but if you have Y on the stack, go to S2. The third, if you have X in input, don't read the stack, go to S3. Okay? That means that basically you can choose not to read either the input or the stack, but if you read it, and you have two transitions which agree in the reading, then you take them both together. Okay? So of course, if you have two transitions which say read X, and then one transition says read Y, and the other transition says, okay, don't do anything. Of course, if you read X and you have Y, you will take both, okay? Because one is just saying ignore the top of the stack, follows this transition no matter the top of the stack, okay? So this is what non-determinism is about. If you remember in the DFA, the only non-determinism was, well, because you only have between one state and the other, the only way was to add a transition like this, right? So, for example, you will take these two transitions together. And it is actually the same reason, right? This transition here is just saying ignore the input. No matter the input, take this transition here. And if you read X, go through this transition here. So both transitions are taken at the same time because they don't disagree, okay? If you had something like this, then of course, if you read X in input, this and this will disagree, so of course you have to choose one. But this one is just saying ignore the input, so it doesn't disagree with reading something, right? So this is how you add non-determinism in a push-down automaton, and now we can go back and actually understand what's happening here. Let's see if we find this. Oh, okay. We have plenty of time. So, what's happening here is that because you have no idea, so I'll remember to you what the language was. The language is the language of palindromes. The problem of this language, when you show it, when you show a string into a machine, is that whether a string is a palindrome or not depends somehow on the middle of the string. So if you can find the middle, it's really easy to check if the string is a palindrome. If you don't know the middle of the string, then you cannot decide, right? So what this push-down automaton does is, well, instead of saying, okay, I know the middle of the string, it just says, okay, every time I read something, I'll assume is the middle of the string. So I span a process and see if I can pop all the symbols I pushed. So let's have an example, okay? So let's have 1, 0, 1, 1, 0, 1. So first I push the end of stack symbol. Then I have a 1. I push a 1. Now things are different, okay? So I'm here, I read a 1, I push a 1. But at the same time, I have a transition telling me, no matter what you read, go here and try to pop stuff. Okay? So, you have two processes actually. You have this one, so you just popped a 1, pushed a 1, so you read a 1, you push a 1, and then you have another process. Here, this is the start, let's say. You have two processes. That is not pushing anything, but is actually following this transition here. So it's actually going to the pop if match state. Okay? And now this state doesn't know what to do. There's nothing here. Okay, you're not reading a 0, you're not reading a 1. Actually, you push a 1, and push 1, you stay pushing. Oh yeah, it's actually wrong, because at the first time step you're actually pushing, so you need 2 symbols to take the transition. Something wrong. Can you see what's wrong here? Because what I'm seeing is that I'm pushing a $, then I push a 1, so I'm here. But at the same time I'm here. Oh, of course, because now I keep reading stuff, right? Yeah, exactly, sorry. So I have one process which has the $, right? So I go here in pop-if match, and here actually I have no reading, so I ignore the input, I find the $match, and I go into accept state. So as for now, this is actually accepting, this branch is accepting, but I am now reading a 0, and that's a problem, because okay, I'm in an accepting state now, but I have no transition to anywhere else. So I'm reading a 0, and I don't have any transition telling me what to do with a 0. Okay, so actually I reject, so I crash. My PDA is crashing. Yeah, it's quite hard to keep things parallel in mind. So let's go to the other process. So I push the 1 into the stack. Okay, now I read a 0. I push a 0 into the stack. But of course here again, I'm spanning another process going through here. And here is happening exactly the same thing. So this process initially goes to, actually this doesn't go to accept. No, this doesn't go to accept because I read a 0, but I have a 1 here in the stack, so I crash anyway. So okay, this is what's happening anyway. So at every input you span. It's a little bit so. At every input you span another process trying to pop things on the stack depending on the input, right? But until I reach the middle of the string, all my attempts to pop will result in a crash, because either I reach, either I pop too little, so I still get something in the input, or I pop too much, I pop even the end stack, and then I don't accept anyway. So the only way this machine is going to accept is if actually, so at this point here of the reading, I'm spanning, well, let's say we're here, I'm spanning the right process. So here I'm doing the right guess. Once I reach the 101, I'm spanning a pop-if match process, let's say. So I finally find the middle of the string, I start popping, I pop all the symbols in the stack, and I finally accept. So all of this is just to convince you that this PDA is actually accepting all palindromes. Okay? So the way it does it is not the most efficient, probably. So if we had a Turing machine, so if we had random access memory, we could, count the length of the string and just say, okay, go to the middle and start comparing. Okay? So if we had a random access memory, we could do that easily. In our case, we just have the stack. So we just can read the top of the stack. So the only way we can accept palindromes is by spanning many processes and trying to guess the middle of the string at every time step. Not super efficient, but still I can accept the language. So this language here of palindromes is context-free language. This is non-determinism. So any questions about non-determinism? So it's clear. Oh, okay, that's cool. I did some confusion right there, but it's smarter. So, we build these computing machines, okay? And depending on what we add, what capabilities we add, we get more or less computational power. So we can compute, we can accept more languages if you want, we can solve more problems, another way to see it, or less problems. So what happens if we restrict the alphabet of a PDA to a single symbol, so a pebble, a stone, okay? So the only thing I can do is put stones in a stack, and then I pop them. So what I'm doing is actually just counting. So the only thing I have is a way of keeping count. So if we do that, if we just restrict the symbols to only one, we get a counter. So it's not a PDA anymore. Well, it is also PDA, but it's called a counter, okay? And it turns out it cannot solve all problems, all context-free problems, all context-free. It cannot accept all context-free languages. Well, that's obvious, right? For example, if we take the language of palindromes and we only have one symbol that we can push into the stack, we can count, you know, whatever you want. You can count whatever you want, but you'll never be able to figure out if the second half of the string is mirroring the first half. Counting doesn't help you. In many problems, counting helps. The first example I showed you, I think it was a counter. Let's see, I don't remember actually. Yeah, so in this case, the only thing you need is a counter, okay? Just need to count. So I saw 10 zeros, now I need to see 10 ones. Just need one symbol, just need a stack, and you put pebbles, and that's all, okay? But of course, if you have that, you cannot solve all context-free problems, so you lose power. So we have what if we let the machine move on the input tape? Actually, we add power, okay? So you see, every time you add even the smallest additional capability, you can see that you can solve more problems, right? With PDAs. So if you give the PDA the ability to go through the tape, even if your stack is random access, sorry, it's not random access, but it's first in, last out, you can still solve more problems than a normal PDAs. So this is called a two-way PDA, and you have two-way and PDA, non-deterministic PDA. And this kind of PDA can solve more problems than PDAs can. Okay? So this deterministic two ways automata can solve more problems. Why I'm telling you this? Because, okay, up until now, if we had, so for example, we take a DFA, the simplest computing machine, we have the stack. Okay, we can solve many more problems. Okay, we get a PDA, so we have a stack. We add the capability to run onto the input stream. Instead of just getting the input symbols, you can go and on the input stream wherever you want. And you get more power. But there's an upper bound, as I told you, for basically the whole of the first 2 lectures, maybe 3 lectures. So there's an upper bound. At a certain point, you add something, and you get the same power as a Turing machine. Okay? So if you add 2 stacks to a PDA, so you don't have only one, but you have 2, you get exactly the same power as a Turing machine. And once you reach that, there's nothing else you can do. You can add rockets. You can add a machine gun. You can add a night visor. You can add that. But if you wanted, you would still be bounded to the power of Turing machines. So once you reach the power of Turing machines, you reach the point. There's no way you can solve more problems. You solve all the problems that can be solved with digital computing. All the problems that can be solved with digital computing, you can solve with Turing machines. If you have a problem that cannot be solved by a Turing machine, guess what? You cannot solve it with digital computing. And that's it, basically. So, why, if we have two stacks, you have the same power as a Turing machine? Well, basically, what a Turing machine does is you have random access to the tape, right? So you can read the tape. And you have unbounded memory, which you have random access to as well, okay? So you don't have, it's not like a stack. You cannot only access the first element. You can access whatever element you want, right? So, well, if you have a two-stack DFA, so you have these two stacks, what you do basically is, remember that these are unbounded in length, okay? You take your input symbols, you put them all on the stack. So let's say you read hello, and then hello, okay? You put it all on one stack, and then you treat this as an input tape, okay? So here, you can push it and pop it on the other stack. You can do the opposite. So it's like you're skimming through the input tape, right? So it's like you get your input tape, you put it on the stack, and then you can go wherever you want, exactly like a Turing machine. So basically, if you glue these together, you get a Turing machine tape. So you can move wherever you want, and you have random access to the input. And in the same tape, you can memorize stuff. So you have random access in the memory. So it's a Turing machine, okay? Same thing goes with if we use a queue. First in, first out queue. First in, first out, yes. A first in, first out queue. Why? Well, just add end of the stack symbol in the beginning. You push whatever you need to push, and then it's like a chain, okay? If you have to push it, if you have to pop an L, you can push it on the back of the queue. Maybe you want to reach again that L you read. Well, you do the opposite, and you get a Turing machine. Okay, that's exactly the same. So your access to the input is random, and you can put as many symbols in your memory as you want, and it's random access as well. So you have a Turing machine. So let's do 10 minutes of break, and then we start with some exercises. Let's do some PDA, so pushdown automatas. We will just deal with non-deterministic ones, because of course they're easier, and I mean they're a little harder to understand, but they're easier to implement. So if you want to find a solution with a PDA, it's very often easy to find a non-deterministic one solving the problem. And of course, if it's a context-free language, you're not sure to find a deterministic one. So the first, okay, these languages are all on alphabet 0 and 1. We did some grammars last time on this set of exercises here, and now we'll do the PDAs. So W contains at least 3 ones. So it's the PDA. It's the PDA recognizing the language of strings which contain at least 3 ones. Is it possible to find a PDA for that? I ask you this question.
Yeah.
Yeah. Why?
Because you
Actually, because it... Exactly. Very good. So, because you can count 3, okay? You can create a PDA which counts to 3. Okay, if you have a number, you can create a PDA, a DFA for that, because you just need a finite number of states. The problem is when you don't know how many states you need, right? But in this case, you know. So DFA will be something of the form 1, 1, 1, this accepts, and then 0, 0, 0, right? So every time you see a 1, you go up a state. You see 2 1s, you go up state, and then you accept, and then you stay here forever. Okay? So this is a DFA, and of course, because we have a simple DFA that solves the problem, this is actually a PDA which leaves the stack alone. Okay? So this is a PDA. You can add a stack to this. You just don't touch the stack. But of course, because I want you to learn something, so to actually deal with PDA, we're solving this problem the ugly way, the wrong way, the inefficient way that makes use of the stack. So one way to do that is, as you say, you push once, and then you pop 3 times. So you have a state where you just pop, push once every time they occur, right? So every time one occur, you keep it in memory. You keep another one in memory. You keep another one in memory. Then you pop 3 times. If you end up with an empty stack, fantastic. If you end up with an empty stack symbol, fantastic. If you end up with some ones, great. It means that you have more than 3 ones. If you end up wanting to pop more, once you reach the end of stack symbol, that's a problem. It means that you don't have enough ones in your stack. So let's implement this. So we want something that pushes ones in the stack every time in the input there's a 1, right? So, well, first of all, you have a transition. You have this transition here. If you have 0, you don't do anything. If you have a 0 in input, you don't touch the stack. You don't do anything. You just stay in the initial state. This is the initial state. If you have a 1, what do you do? Exactly. So, okay, let's say that the stack symbol, the stack alphabet, is just symbol 1. Okay, it could be a stone, it could be whatever. It's just a counter. So you need just one symbol, right? So let's say that if you have a 1, you don't read the stack at all. You just push a 1, or if you want a star, it doesn't matter. Well, let's do a star. Let's see. It's nice to draw. So. Let's make it non-deterministic. So at every step of the computation, you try and pop 3 times a 1, okay? So if it fails, well, it fails. If it succeeds, then accept. So what you do is, you have you have a transition like this. Let's make it simple. So at each time step of the computation, you also are here trying to pop ones. And well, here of course you have 3 states. 1, 2, 4 states, because you need 3 transitions. This is an accept state. Here you don't care about the input, but if on the top of the stack you have a 1, you pop it, okay, and you don't push anything. Same here, you don't care. If you have a 1, pop it, don't do anything. Oh. E1, okay. So if you manage to, actually we didn't even need the end of stack symbol, right? If you manage to pop 3 ones, then you accept. If you don't manage, you end up somewhere here, And actually here, because we want to stay here forever, we just say if 0, do nothing, if 1, do nothing, right? Yeah.
Could you not just pop on that first transition and make it 1 shorter?
Yeah, it's just for clarity.
It is, okay.
Yeah, just to say, here you start popping, here is a push state, you know, just, but yeah. So we solved this problem, really easy. It's an overkill, you don't need a PDA to solve this, but you have it, so. Actually here, I used ones, but we were dealing with stars, so let's put some stars. Just to make it very clear that the utility of this is just to keep count, so it can be anything. It's just a counter, okay? So I didn't give you any formal definition for the PDA. You can find it in the book. You can find it just in the book. I think in the notes, Sarah didn't write anything about it. And, yeah. If you're interested, you can find the formal definition in the book. But of course, now you should have the hang of it, right? So a PDA is nothing but you have an input alphabet, you have a stack alphabet, which doesn't have to be the same as the input, as I showed you. And then you have states, and then you have transitions, and then you have an accept state, or a set of accept states, and an initial state. So what you add in respect to the DFA is a stack alphabet, and you modify the transition function so that instead of dealing with just input, it deals with input stack and manipulation of the stack. Okay? So that would be the formal definition. If you actually want to read it, it's on the Michael Sipser chapter I uploaded already on the portal. So let's go with the second problem. W starts and ends with the same symbol. Yes. Can this be solved by a PDA? Why?
Just put the first symbol on the stack and then check at the end if it's...
Yeah, exactly. And again, this is a DFA. You're the DFA expert. So it is a DFA. Why? Well, let's do it. If you start with a 0, you go here. If you start with a 1, you go there. And let's say, well, these are accept states. If you then have a 1, you go somewhere else, which is not accepting. If you then have a 0, you go back. And the same here. If you have a 0, you go somewhere else. If you have a 1, you go to the accept state, right? So if you start with a 1 and you end with a 1, you're free to go. You're accepting the string. So that's good. But again, we want to do it the PDA way. So as you said, you push your first symbol on the stack, and then something non-deterministic pops it. And if it finds the end of the stack, then it means, if it finds, no, nothing like that. You just push the first symbol and then you pop it. And, if it works, then you accept, right? So, start. If you have a 0, you push it. If you have a 1, you push it. This is here you're just pushing the first symbol on the stack. So you have it here in memory, and then something happens, which would be if you have a 0, do nothing. If you have a 1, do nothing. And then, non-deterministically, if you have both a 0 in stack and the input, you pop it, and you go to an accept state. So how does this work? So here we're using non-determinism. So we're making our life easier. So at every time you're here, at every time step, you check that the symbol you're reading is the same you have in the stack. If it is, then you go into the accept state. If you keep reading inputs, here you crash. Okay? So if you keep reading symbols, you don't have anywhere to go here, you don't have any transition, so you crash. So that means that you're not accepting, you're rejecting. But if you finished with your input tape, if you're finished with your input string, it means that you stay in the accept state. Actually, well, if we define starting and ending with the same symbol, for example, I could say that 0, the string 0, starts and ends with the same symbol. It is actually true. So this PDA doesn't capture that. We just add one transition like this. So 0, 0, sorry, 1. But what does it mean? Well, non-deterministically, if you have only one symbol, you just go to the accept state. If you have more, here you crash, so you don't accept, so you're happy. Here's another. So the length of W is odd. Can this be captured by a PDA? Can this? If I give you this problem, can you think about a PDA which solves it? Well, think about a DFA that can solve it. Do you have a DFA that solves this problem? So, yeah, of course you have, right? It's very, very easy. It's a simple problem. So if the length of the empty string, if the length of the input string is odd, it means that you have something like this, right? So if you have one symbol, you accept. If you have two, you reject. If you have three, you accept. It's very easy, right? Again, let's make it interesting. So, a possible algorithm is you keep a symbol on the top of the stack, telling you if up until now you're seeing an odd number of symbols in the string or an even number in the string, right? And every time you read a symbol, you change the top of the stack. So let's say you have 3 symbols. So you read the first one, you read the second, read the third. So this is, okay, let's make it like this. So if the hand is on your direction, I'm accepting. If it's in my direction, I'm rejecting, right? So let's start with this. I have 3 symbols. So I have 3 symbols. So I read the first one, second, third. Yeah, I'm sorry. So I start with even because it's an even number. So this means odd. This means even. I start even because no symbols is an even number of symbols. 0 symbols. So I read 1, I read 2, I read 3, and I'm accepting. Sorry for the middle finger. So that's exactly what I'm going to do, right? Well, this is really an overkill one. Let's say something like this. So if I read a 0, yeah, we need the end of stack symbol. Or we could just start with a symbol telling me I'm starting even. So let's say that I have 2 symbols in the stack. One is E, meaning, okay, up until now the number is even. And one is O, meaning that the number is odd, right? So I start with the stack having an O in it. So this is the starting state. and we push an O in the stack. And then if we read a 0 or a 1 and we have an O in the stack, we change it into an E. At the contrary, if we have E, whatever we read, we change it to O. And maybe non-deterministically, yeah, if we read an O in the stack, we just go to an accept state. Seems like it works. Seems to me it's working, right? So, every time I receive an input, I flip this bit, let's say, okay? And if the bit is flipped on the right side, so I have an odd number of symbols, I accept. So that's a way to use a PDA for this problem, which is already an overkill. But, you need to make practice of it. Okay, now I think we're starting with the interesting ones, the interesting problems. So the problems that can only be solved by PDA, right? I'm deleting this, but I'm going to regret it. So we need to redo it for the port. Okay, so the length of W is odd, and its middle symbol is a 0. It was exactly like the previous automaton, the previous PDA, but instead of having a non-deterministic let's have a look. So the middle symbol is a 0, right? And the length is odd. So it means that, yes. Okay, you flip the bit in the stack every time you read the symbol, right? And because the length of the string is odd, okay, so you have a 0, and then you have stuff here, right? Both before and after, you need an even number of symbols, right? Because even plus even is even, plus 1 is odd, always. Okay? So what you need to do?
When you see a 0 in pop.
Sorry?
When you see a 0 in pop and it's even.
Yeah. 0 pop. Let me think.
Yeah, if you add something to the stack each one at the start, and if you see a 0, you pop, and then you can afterwards.
Yeah, that transition. So it was exactly the same automaton as before, but instead of the odd transition, you also have a 0, right? So you read 0, you read odd, and you accept. And then the problem is that you have this middle thing here. So what you want to do, I think you have
the palindrome one.
Yeah, it's exactly the same. So it's the palindrome automaton, but you have a 0 in the middle.
And you're looking for odd and not even.
Yeah, exactly. Yeah. Okay. I want to write it down because I'm sure I will get it wrong. So you want me to write it down? Okay, let's try. Exactly the same number. Oh well, then it's not like the other automaton. You have to push. Okay, let's say you push an end of the stack symbol, then you start pushing the other ones. So you cannot use a counter here. You actually need a 0 and 1, right?
Yeah.
Yeah. So If you have a 0, you just push it. If you have a 1, you just push it. Yeah. And if you have non-deterministically, if you have a 0, you don't do anything. Oh, you don't do anything, and you start popping. If you have a 0, yes, if you have a 0 or 0, E or 0, oops, 0, 1, it doesn't matter. Is that right? Okay. 1, 1. You pop. At a certain point, you find the end of the end of the stack, and you accept. I think it's right?
Yeah.
No. Okay. That's good. Okay. Oh, the pattern one we already did, right? So the empty set we're not, doesn't matter. Okay. This is G. I think I didn't actually write it down. Oh, okay, that's all right. So, as at 0 in every odd position. Well, again, here I think it's a regular language, because all you need is 0 or 1, doesn't matter. You are, oh no, sorry, it's an odd position, so you accept 0, and if it's 0 or 1, you, yes, and if I, yeah. So this is actually a regular language, right? I don't think you can read it. So, smart. Just delete this. Okay. So this is a regular language, and so we can have a DFA, and I actually want to. I want to do the PDA for this. I want to do the grammar. Okay, let's do a left linear grammar for this. So you learned how to do that. How do we go about it? So we want a grammar describing the language of strings that have a 0 in every odd position, right? So we have our DFA. How do we go about making a grammar out of it? Do you remember the algorithm?
If you're in position A, you receive a 0.
Sorry?
If you're in state A, you receive a 0. Then you go to state B. And after that, if you're in state B, you receive a 0 or 1.
Okay.
Go to state A.
Perfect. That's exactly that. The only thing, instead of calling state in case of grammar, is a variable. So, yeah, in a left linear grammar, in a grammar you call it variable, and this left linear, so we have 0 B, right? And then you in B, and then you can have 0 A or 1A exactly, 1A. We're missing something. I think. Yeah, we are. Which is something in A, right? No, something in
B.
B.
The empty one.
Yeah, exactly, the empty string. So this is our left linear grammar. So hopefully this should be super clear to you, and we can start with the good ones. So now our language is A to the M, B to the N, such that N is not equal to M, meaning that either you have more B's or you have more A's, but you don't have the same number of B or A's.
Surely that would be the same as previous one. In a sense, because it's just valid numbers, and it doesn't matter what input you get, since it's not even.
No, I don't want to do a PDA now. I want to do a grammar. Okay. So But yeah, it's actually pretty easy. So because of a PDA, you start pushing the A's, and then you pop. You pop for every bit you read then. And if you end up with the end of stack symbol, you reject. Otherwise, if you're popping too much, perfect, you're okay. If something is left in the stack, still okay.
Yeah. But it's also the same as the DFA we just did, because if it's not equal to M, then it's got to be or not even. M doesn't equal M, it's or.
Well, no, the problem is that here you need first all A's and then all B's, right? So this notation here means A, up, B, up, these M times and these N times, okay? So in the case of the grammar, what you need to do basically is actually very simple. How to generate such a language, okay? Well, think about an algorithm. So if you want to generate this kind of strings, what you do? What I will do would be to first generate AB, okay? So balanced ABs. And then when I get to the middle, I just add some A's or some B's, okay? At least one A or at least one B, or maybe more, okay? So I can use recursion. So for example, a grammar would be something like that. A, S, B. Yeah. Or A or B. Yes, I think it's right. Right? So with this, so this one recursively adds A and B's. And they're always balanced, okay? But at a certain point, you want to unbalance it, so you either add an A in the end. Oh, but actually, maybe you want more A's, right? So let's put some variables here. Like A becomes now A empty string. No, this is not good. A or A, yeah, perfect. B or B. So what does this mean? That here, so you get your balanced string, and then you have something of this form here. Let's say A, B. So this is equal to this, and you have an S, right? And you want to unbalance things now. So you have to add at least one A, or at least one B, or maybe many A's or many B's, okay? So what you do is, this becomes, let's say, this becomes an A. You want to add more A's. So A can become either a single A, so you're already unbalancing it, or it can become more because you have also the rule A, big A. So this can be 2 A's, for example. Okay, or 3 or 4 or 5. And the same is true for the B. It's exactly the same rule, right? So you have more B's.
How do you finish that one?
Sorry?
Don't you need to finish it?
No, you don't need a B, because basically, in the end, right, what you want to produce is a string of all terminals, meaning a string of everything that is not variable. In this case, A is a terminal. So for example, in this parse tree here, which is not a parse tree, something that doesn't have before, you end up with the A, B, right? You don't have variables anywhere, so you're happy. Okay? So the empty string we use the empty string as a way to eliminate a variable at some point, so that you end up with only a terminal. This is this. As we say, the PDA is you just have to do the exact same thing we did before. So you count the A's, and then you start popping, and you don't accept only if you find the end of string, the end of stack. Otherwise, you accept. So I won't draw it with an exercise which was almost exactly the same. So, oh, this is a nice one. Hope I read it down because I remember it was lengthy. There's 3 ones. Okay, this. Yes. Okay, so we're solving A to the L, B to the N, C to the N, so that either L is not equal to M or M is not equal to N. So I will first produce a PDA. Okay? So let's first do a PDA and then we do the grammar, okay? So we have two problems that we know how to solve. This is exactly the same problem as before, right? If we ignore the C to the N, this is just making sure that there are either more A's or more B's, okay? But not the same number. So the PDA in that case would look something like, I finally write it down then. So you push your end of stack, then you start pushing A's, and so you push all the A's you can. At a certain point you meet a B, and you start popping basically. You start popping, and then you keep popping. Okay, and then at a certain point, you should find the end of string, the end of stack. So this is an accept state, okay? Meaning that you push a lot of A's, then you start popping B's, okay? And yeah, if you're here, it means that you have still B's to pop. So it means that you didn't yet count as many B's as A's, and that's good. If you do count as many B's as A's, then you don't accept. And maybe if you're still receiving B's, you accept, and you're actually happy. So here, whatever you do, you stay there, right? So you counted. There's more B's than A's, so you're happy. You accept. But okay, this was actually the PDA for the former problem we solved. How to solve this one? Well, from the PDA point of view, it's very easy. We just tap into our non-determinism tool. So we say, okay, keep pushing A. It doesn't matter. No, actually, yeah. So we have a non-deterministic transition which says if you read anything, don't do anything, just come here. And here you do exactly the same thing. You start pushing these, okay? You start pushing these. At a certain point you meet an X, a C. If you meet a C, I'm using two different notations. Here you have an X. It's right, yes. So if you have, well, you have exactly the same PDA as before, okay? But mirrored here, okay? So what you do is basically, at every time step of the computation, you ignore whatever is going on, you assume you're getting to the B's, and you start counting the B's, and then you make sure that the B's are either less or more than the C's, okay? And the only way this can go wrong is if the number of A's is equal to the number of B's that is equal to the number of C's, because it means that the PDA, the two processes spanned will be one here and one here in the non-accepting states. Okay, so it means that you reject. In all other cases, it's good. You accept. So this is the PDA. Let's do the grammar now. So what you want is, so you have a starting variable, and you want something of the form like this, A, B, C, and then, yes, I believe this is right. So, in a way, it's exactly the same problem we solved before. You just use the same technique 2 times. Okay? So here, S1 again is adding the same number of A's and B's. So you're creating a balanced number of A, B's, right? Here. Up until now, you're creating a balanced number of A, B's. Okay? And as we did before, we can then create either more A's or more B's with these variables here. So A, or A. B, big B is equal to B, big B, or B. So this is the same thing we did before, right? So we keep recurring. We have something that is balanced, and then at a certain point we have to unbalance it to reach a terminal. Okay? But of course here we also have this added complication, but it's actually easy. We have S2, we do the same thing, so we balance, we have something which is balanced, and then we need to add more B's or more C's. Exactly the same thing as before. Okay? With this we are assured that in the end we get something which either A's, there are the same number of A's and B's, but there's a different number of C's, or there's the same number of B's and C's, but there's a different number of A's. That's exactly what we wanted in the first place. So this is the grammar. So is there any question? So if something is not clear, I'm happy to. Okay, let's do the last one. Oh, this is really easy. So we had a difficult one, but this is actually easy. So A, the new language is A to the 3n, B to the 2n. What does this mean? It means that for every 3 A's, you have 2 B's. Okay? So if you have 6 A's, well, it means that the number of A's is a multiple of 3. And for every 3 A's, you have 2 B's. Yeah, that would be a good description. How to solve this with a grammar? Well, really easy. Can you give me a hand? So you want something that produces multiple of 3 ASB.
What would it be? AAASPB. Very, very, very good.
Let's say that n is more you know. Otherwise we just have the empty string. Oh yeah, you have to add that. So we have A, S, B, B, or empty string. Is that right? So if n is 0, you have the empty string. Otherwise, you recur, and of course, you are sure in the end to have even number. Sorry, a multiple of 2 B's and a multiple of 3 A's. And for every 3 A's, you have 2 B's. So now let's do the PDA. The PDA, you have something like that. So let's say you have a starting state. So you want to count. Well, let's push the stack, the empty stack symbol. So now what we want to do. So do you have any idea how to solve this using a stack? So you have to count. That's evident, right? How to count? How to make sure that there are 2 B's for every 3 A's?
Every time you've added 3 A's, you push 1 count into the thingy, and then you've added 2 B's to the top.
Almost.
Or then you pop, sorry, every time you've taken 2 B's, pop.
Yes. Let me think. You have 3 A's, okay? So you want a transition that makes sure you always have a multiple of 3 A's, right? And then you want every 2 A's, you push 2. And then every time you meet a B, you pop. And then the problem is solved, right? So you want something that says, I always need a multiple of 3, multiple of 3 every time, right? Of A's. So if I read A, don't do anything, push an A. If I read A, don't do anything, push an A. And here, if I have an A, I don't do anything. So with these, I'm making sure that there's a multiple of 3 A's, right? Because otherwise, if I start with B's here or here, I just crash. So here I make sure. But then I just push 2 A's every 3. This way, I'm keeping count, and I can pop the B's and make sure that for every 3 A's I have 2 B's. And that's problem solved. So for example, we can be deterministic here. Make sure pass to the second part of the process, which is just popping B's. So if I read a B, I just pop the A, and then I'm happy if I reach the end of stuck, and I accept.